Hello everyone, October 26th. Alright, get right into it. Image overlap. You're given two images, presented as binary, square matrices n by n. A binary image has only 0, 1. We translate one image, however, we choose by sliding all the 1 bits left, right, up, and all down, any number of units. We then place it on top of the other image. We can then calculate the overlap by counting the number of positions that have 1 in both images. Note also that a translation does not include any kind of rotation. Any 1 bits that are translated outside are erased. So we have two images. What do we want to do? Return the largest possible overlap. Okay, so that's the image 1, image 2. We translate image 1 right by 1 and down by 1. Have a 1 in both images, so that's a 3. Maximum overlap. Nah, not even the maximum. We can also move this. That'll also be 3. My God. Can't you think of a better 30, a better test case? So I have one example to work with. I can think of other examples. So we want the maximum overlap. So definitely it will not be the one with a larger number of ones, right? Because to translate, you only decrease. And then the maximum we can get is the smallest. So we can, and moving one to fit the other, I'd rather moving the small to fit the big. But at the end of the day, it's the same, right? So we move the small, trying to fit the big. It's the same as move the big, try to fit the small. But if we have a final image that they overlap, then it's the same. So for me, it's easier to think about moving the small to fit the big. So now we get the small, and now we get the big. What we want to know is the shape of the big, right? And then we're trying to say, with the small, we also have a shape. I mean, what we can do, because only 30 by 30, so we can try out every single possible position actually. I think, yeah, it's only 30 by 30. So what we can do, we get, but every one has to move. All the 1 bits will move. So basically, we say for whatever we have, and all possible moves is if we say, what are all the possible moves? Well, we have this entire thing, right? If we can go all possible moves, then we can always find the largest. And how do we find all possible moves? Well, when we move it outside, that would be 0, right? So let's say, man. So with all the images, right, actually it doesn't really matter which one I move, it doesn't really matter. So with all the images, I can move but always the top left and bottom right, right? So the maximum move is the bottom right, move to the top left corner. And then we can go move right, and then down, and then down, and down, and down. And then basically we'll extend the whole thing, right? And then we can move all the way until at this level. Yeah, so we find the lowest position, right? And that position will be the top left corner, no, bottom right corner, the bottom right. So the bottom row of the image, right? And in the bottom row of the image, we'll find the rightmost position, and that will be thrown into the top left corner, right? And then we will just move right until the left hit the top right corner. So that's that, right? We've done that. And then we move down, right? We move down. And when we move down, now we have to consider to move to the left again. It should be as left as we can, which should be the rightmost, so the biggest, right? The biggest between these two, that should be start. Yes, that's at the top left corner. And now we go, okay, and move down, and that's that. No, it's just the biggest, oof. The biggest of them should put it there, and then we start the scanning, right? And then we scan. Holy guacamole. What would be a faster way? Why don't you just move the entire thing? Hold on. Why don't you just move the entire thing? And that's 30, so I can turn that into a binary number. 110, 010, 010, right? So it's an array of 3 values. And then we're gonna move, right? So we say the bottom is gonna be here, right? So we're gonna just this. And the total number is this, and yes, it's and this, right? We want a maximum. So yeah, it's fine. We can just, whatever this value is, we can left shift, right? So that I will right shift. No, we shouldn't right shift. There's a left shift. We just want the tail. How do we get to the tail? We get to the tail by okay, we can get to the tail. So we do this, get a tail, left shift, right? Left shift, so we become this, we end, and we end, right? And all the end value. So we end, then we're going to count the number of ones. And I'm going to count the number of ones. Yeah. Now we move to the right. And do the same thing, right? Do the same thing. Yeah, and then we move down and do the same thing. Move down to the same thing. We move all the way down to the same thing. Now, as we move to the right, the state is the bottom right position. Okay? So if it's smaller than this on the left, if it's larger than this, right, whatever this value is larger than, then we need a right shift. Right shift and. Ooh. Okay, we can try. Oh, this one's not easy. A lot of moving parts. But basically just it's gonna be brute force. Right, we're gonna brute force this thing, but it can be made a little bit smarter, right? A little bit smarter. Okay, so n equals len image 1. Doesn't really matter because these are the same. And yeah, they're all the same. And then we're gonna turn bitmap 1 equals to. So how to turn this into bitmap? A row in image 1, right? I don't know what would be the easiest way to do this. And for each row, we can sum, or we can convert. Maybe sum is easier. So for each row, right, and then, sum something, right? For each row, we just sum and say for I value in enumerate row, you value left shift I. And we sum this. So this is bitmap 1. Oh shoot. And then we can do bitmap 2. Basically it's the same thing. Alright, we need to check. Let's put this one down. Yeah, this one I have to go step by step. Yeah, these are trivial cases. And then these will comment it out. Image 1, image 2. Let's print this out. Okay. That's not right. That's not 3. That's 110. No. Something is very wrong. A row in image 1, right? It's 1, 1, 0. And for I and a value in this row, oh, shoot. Like this image is the inverse. Damn. Well, it's fine, but because we can do n minus 3 minus 0, we'll go 3, actually minus 1. Right? It's not a big a deal. Yeah, 6, 2, 2, 0, 3, 1, yeah. Okay, so bitmap is ready. Now it's just going to be this one. We're going to start from this position, right? And then we're going to move 2 more, so this can end line here. So we know how many we have to go. So from this, basically n plus n minus 1, right? N plus, I have to do 2 more. N minus 1 is the total number of steps it needs to go. And then it has to go down the same thing, right? Don't go down the same thing. Okay, so with this, we say go down for I in range. So what will be the range? Let's think about the position, right? So we start with 0, 0, 0, right? And 0, 1, 2, right? And all the way to 2n, 2n minus 1. That'll be 5, right? So 2n minus 1. 2 times n minus 1. This is on the I, how many we have to go. And then for j in range, 2 times n minus 1, right? Because j goes from here and all the way to this, right? We have to go like that. Okay, so with this, now we have to find out, oh man, we have to find out at each position, right, at each state, what are the ones that's kind of inside, right? So we say if j is smaller or equal to n minus 1, right? If it's smaller or equal to n minus 1, that means we have this part, right? We know this part, so we can get yes. And if I is smaller or equal to n minus 1, that means it's going to be this part, okay? So we probably do I first, so we know which one will be involved, right? So for here, I basically just, we know the ones that's going to be involved in here, right? We know the one's going to be involved in here. So let's do damn. Yeah, let's consider the two situations. Let's consider if I is smaller or equal to n minus 1. Okay, and then else means I is down, so we have to consider differently. So now I have 2 more situations here. If j is smaller or equal to n minus 1, right? Else. Then the same thing gonna happen here as well. Okay, so now it's I is just basically it's inside here, right? It's inside here. So if it's inside here, then we can find these, we can find. So basically they will just be from 0 to I. Well, 0 to I plus 1. Can get that value. Not too difficult. And then what? Then we have to get, because I want to move image 2 onto image 1. That doesn't matter, we can move image 1 on image 2. Let's move image 1 to image 2. So we'll move image 1 to image 2, and it's like here, right? So we can get, so basically coordinates is for this, right? So if it's 0, if I is 0, so the other one is going to be 3 minus 0 minus 1. So it's n minus I minus 1, right? N minus I minus 1. And from m minus 1, hold on. The m minus 1 minus 1. Yeah. N minus I minus 1 is the top. From n minus I minus 1 to n, right? These are the two. So we're trying to get for I, right? So for I can say, my God, for I in range. So this is trying to get the image 1, right? So that will be n minus I minus 1 to n, right? This is the I range. Right, so for this is the I, for each one we need to compute the actual thing. So we can say bitmap 1 II, right? That's the one we get. And we need to do some shift. So we need to, this thing need to and, right? And something, a mask, right? And then this mask, because if we're doing, let's say this, right? The mask is going to be, how much is involved? How do you know how much is involved? Involved, the number involved is j, right? The j is involved. And then we're going to say 1 left shift j. Okay. Now, 1 left shift j plus 1. So if we have 2, it's involved as 0 is 1, j is 1. So we say 1 left shift 2 minus 1. That is the mask. So we're going to say 1 left shift j plus 1 minus 1. This is going to be the mask. Right, so this is the one that's overlapped. Right, it's overlapped. But then this whole thing we have to left shift because we have to get this. So left shift how much? N minus j minus 1, right? Or just n minus j. Oh, j is, over here, j is 0, right? If j is 0 and n is 3, 3 minus 0 minus 1 is 2. So basically this need to left shift 1, 2 positions. Yeah, that's actually right. So if we're here, j is 1. 3 minus 1 is 2, 2 minus 1. So we need to only left shift 1. So that is the bitmap. That is the first image. So we need to do this thing, right? This thing need to and something, and this image 2. So bitmap 2. Now bitmap 2, the position is actually just I, because it's going along, right? So that will be the right, that will just be, we have the result. I want a maximum overlap, right? So this is overlap, overlap, OL. Right, overlap is this and this. Now we need to count how many ones are in there. Right, so this situation, this is each case, and then we say the current is going to be 0, right? And then for each one, we go to 1, blah, 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 done, and we go to the next one, and we redo it. And then we say current will be plus equal to binary OL dot count 1. So that's the number of overlap for this specific row. And then we go to the next one, I go to the next one. So done. That is the first case. Second case, J is larger, so we're moving outside, right? If we move outside, the I is still the same, so we can copy this, right? So we can copy this. Oh, actually, once we're done, yeah, we can do that here. So once we're done, we can say rest equals to maximum rest and current, right? So we can copy this, but this one will be changed. This is actually the same. So we're just saying when we now move out, right? If we move out, then we don't left shift, right? So for this bitmap thing, for this thing, we are handling the front. Then we just simply right shift. That's all we need to do. We just need to right shift. Initially 110, then right shift to 1. So how many right shift we need to do? So just gonna be right shift, right? So this is just going to do a simple right shift. Now J is larger than n minus 1. Alright, so J is actually n, right? J is gonna be here, right? Now if J is here, then this one will be here, so we need to left shift to 1. So it's going to be J minus n, right, plus 1. Because J is larger than n. Well, first J is n. The J is here, J is n. And then will be here, so it will be these two, right? It will be these two positions. So, no. There's this thing moving here. So this is on the outside. So it's these two, right? So it's be this, right shift 1 position, right? Right shift to 1 position. And as n, and there's also n, so n minus n is 0, so we plus 1. And we go more than, yeah, the largest is 2n minus 2, right? 2n minus 2. 2n minus 2, so n minus 2, so n minus 1. So the most is right shift n minus 1. In this case, right shift 2. So 1, 2. Yes, that's correct. So we do this and we do this. Pretty straightforward. And then we do this. And then we do this. Done. Okay. So now we're going to consider this I drops below. So I is now here. Okay? I drops below. If I drops below, which means we're handling this situation, right? If I drops below, what do? Well, I is going to be here. This is the I, so I equals to n, and the top is going to be here. So it's going to be from 0, right? So the I is always going to be from 0, right? It's on top, until what value? Until I minus n. Right? Wait, hold on. I is here. And we need to go to a -1. So I minus n plus 1 is the number that we are out. So we say n minus, right? We just want to know how many are inside, right? How many are inside? That's what we need to know. So this n is the total number minus the number outside. So numbers outside is I minus this. So we get I minus I plus n minus 1. So 2n minus I minus 1. Right? So 6 minus 3 is 3. 3 minus 1 is 2. Right? 2. So it'll be, go here, it'll be 0, 1. Yeah, so this will be 4. I range from the start to 2 times n minus I minus 1. Okay? So for each one, this will be the same. And for this is the same, and this will be the same. Right? Because the j follows the same, and within the j it should be the same. And then we will do return the max. Okay, let's try this. I have no confidence, but oof, list out of range. How's that come to pass? Which one? This one. 2 times n minus I minus 1 is not right. So I is n, right? Is it j? Don't know, man. Just n minus and then to 1, 2 times n minus 2. Oh, let's try. 2n minus 2n minus 2 minus 1. It's 2n minus 2n plus 2 minus 1. And 1 is just 0. Where is the problem? Oh, here is the problem. Damn, I didn't realize that. Okay, so yeah, we're not done yet. So the number on the bottom is I minus n plus 1, right? It's the number on the bottom, which means if I have 1, then with the starting position. So for II, no, we have to based on II. Okay, based on II, it's fine, it's fine. So we have II is at a certain position. And II, what the heck? II is this. So it should be II plus I minus n plus 1, right? Because I minus n plus 1 is how many is the bottom, right? And then II, if it's 0, we have to add 1. So what I think is has to be II plus I minus n plus 1. I plus I minus n plus 1. Yeah, I didn't return. Oh, this one's right. Oh, they're all right. All right, let's see. Let's see what we got. We can actually, yeah, why not? That's only 30. I want to print this way. Okay. It's okay. Doesn't really matter. Wait, randint 0, 1. Yeah. So what we're gonna do is we're gonna create image 1 and image 2. But we need to know. Okay, just print them. For this in range, let's do 10 test cases. Okay, so we're gonna print this and print this, right? So for each one is going to be this. For this in range, let's do 30. Let's do 10. Okay. All right. Each one is going to be for this in range 10. And then this is just randint 0, 1. Okay, and then we'll do exactly the same. So we'll do exactly the same. We're missing something. All right. The worst will be we do it right now, and there's an error. That's fine. If there's error, we reduce the size, and then we have an error. Okay, it's fine. Reduce the size. Let's do 3. Right? Actually, this is a pretty stupid way of doing this. We're gonna say size equals 3. Okay, and then this is gonna be size out of this size. There'll be repeats, but it's fine. Now we can see if everything passes here. Good, we have error. The first one we have error. Nice. Error is a good thing. Helps us. Helps us learn. Supposed to be 4. Yep, that is not right. Okay, let's see. What do we have? So image 1 is 101, 000, 111. Image 2 is 110, 000, 111. So the maximum overlap is, yeah, we shall encounter this, but why we did not? It's actually happening, should be happening here. Right, should be happening here. When j and I are both n minus 1, okay, so if I is n minus 1 minus n plus 1 be 0, right? I be 0 too, that's true. And bitmap, yeah, bitmap, okay, let's see. So 0, bitmap 1, 0, okay. And then this bitmap 2 is 0. That's true. Ooh. Ah. I see. This is not right. This is not I. It's not I. Holy crap. It has to be something calculated from II. Okay, let's see. So I have II. Great. And oh, how do I transfer? How do I transfer? Shoot. Come on. You're almost there. We have this. We know this position, right? We know its index. And then, what's the index on the second image? Should be n minus 1 minus II, right? Because if II is, let's say, 1, nope, For II in this, no, yeah, II minus n minus I, no, we started at 0, right? So it should be II is n minus I minus 1, right? And then we go bigger. So everything should be II minus n minus I minus 1, right? So in this case, if I is 1, right? I is 1, which means we are heading here. And then in 3, yeah, because it has to be 0. It has to be 0. And up to n minus, yeah, so it should be II minus n minus I minus 1. Here, same thing. II minus n minus I minus 1. That's not fun. Yeah, let's do it again. So II is 0, right? Because right now, I equals n minus 1. Okay, I equals n minus 1. I equals n minus 1. N minus n plus 1 will be 0. So it'll be II, right? So it'll be II. This will be II. So bitmap 1 and bitmap 2 will be exactly the same. Okay, which is fine. Now we're gonna say j is n minus 1. So we left shift 0, right? And left shift 0 shall maintain the same value. Yeah. So now it's going to be this. Going to be this. And how about this? J is n minus 1. N minus 1 plus 1 is n. So 1 left shift, I suspect we have to do another parentheses. Gourd. There we go. Yet another parentheses. Okay, let's try this one. Looking good. Okay, let's do size equals 10. So go back to size 10. Try it. Okay, last one. Size 30. So this is the ultimate. Oh my god, so many. Okay, this is the last. If this one passes, we're gonna submit it. No, don't time out for me. All right, this didn't say if I pass or not, but I guess it does. Okay, we can submit. Oh, I've done this before. Done. I thought it's a new one. I don't remember this one at all. Lord. All right, let's see what we did last time. Probably the exact same method. No, I think it gotta be easier than this. Very fun. That's very fun. When it's 2020. That's 2 years ago, man. 2 years ago. During the pandemic. All right, how long did it take? Took 47 minutes today. Not hard in terms of figuring out a method, but very complicated in implementation. I first turn both images into a list of into bitmaps, then brute force it by traversing all possible overlap states. At each state, compute the number of overlapped positions. The difficulty lies in accurately finding out the bitmap to end from both images at each overlap state. I call it O(n) squared, although we can argue that actually it's not O(n) squared though. O(n). This is actually O(n), so actually I'm gonna say O(n) tripled. Yeah. Okay. Let's see, what was the solution? This is today. 59 test cases. Right. This is last time. 49 test cases. Oh, you gotta be kidding me. What was this solution? Just curious. So much easy, so easy. Brute force. Intersect. Oh. Huh. We can, like, true brute forces. Okay. Yeah, maybe I'm overthinking it. Hold on, let's see the solution. Shift and count. Yeah. Linear transformation. I went to the fourth. Yeah, they count this one as well, I guess. Oh, the convolution operation. Kernel, yes. And NumPy. This is convolution. I was actually doing convolution, but what's the key things here? Oh, the shift. Oh, you can sum. Is this the convolution? Oh, it's me. Completely forgot. I was in this before. Be padded. Ah, be padded. So we pad B into this giant thing, and then we just shift inside. Holy moly. Yeah. And then we shift, and then we get kernel, and then we do. Why is the convolution is a multiply? Dot product. A dot product. Ooh, a dot product. Wait. How'd you do a dot product between? How'd you do a dot product between two matrices? Oh, it is every single one. Multiply, 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 multiply. I see. That's the dot product. Holy moly, this is actually a very good solution. So what are these solutions? Linear transformation to align the cells. Wait, hold on. What was this method? The vector one. Find all the ones, then compute the vector needed for two ones to match. The max occurrences of such vector is the max overlap. So we get all the vectors, right? Vector. So we have these are the two ones, and then from B to 1, right? So it has B minus A. So we have this vector, which means if we move from this to this, and we use this vector. Oh, wow. Wow. You don't have to reduce it to the simplest form? I guess not. We don't have to. Yeah, this is the vector. This is the vector that you can use. It points to that direction, right? So from B to A, you go that direction. So those two ones will overlap. And then we say, okay, using this vector, we have 1, right? And then if the same vector occurs again, yeah, you don't have to, because the entire thing shifts. So they have to shift in the vector of shifting is exactly the same. Oh, this is so much easier. God. So that's the vector idea. Now I can reread this. Yeah, this is just 1, 1, this vector. To align them, we do this. Yes. The same linear transformation vector. Yes. Key to group all the yes. Yes. My God, so good. The convolution is actually good as well. I like the convolution as well. Yeah, this is a solution number 2 from the official solution. Find all the vectors that leads that allows a 1 from image 1 to move to another 1 in a 1 in image 1 in image 2. Right? Keep count of this vector. Then, if another pair of 1s in the 2 images require the same vector to overlap, then we know using this vector to shift the image would result in 2 overlaps. Therefore, the problem is transformed to finding the max number of occurrences of any vector that allows the 1s in the 2 image to overlap, to match, to overlap. Yeah, so we should do this, right? Then we need to find the 1's 1. If this 1's 2 is this, right? I'm going to say for I in range n, for j in range n, right? Say if image ij, say 1's dot append ij, and then same thing, 2. Yep. So once we're done, now we're just gonna go say for I1 J1 in 1's, for I2 J2 in 1's 2, vector shall equal to, let's say I2 minus I1, J2 minus J1, right? Then, oh, we need a counter. Oh, we need a counter. Right, and we say counter vec plus equal 1. And then we're going to return maximum of counter dot values. That is not right. And counter is not defined. Of course it's not defined, because I forgot to define it. Let's say if counter else 0. There we go. That's a beautiful solution. Absolutely beautiful. The thing is, it's so simple, right? That's the thing. It is so freaking simple. All right, now we're gonna go for number 3. Yeah, that's all right. Don't really care too much about the time. All right, number 3. So number 3 is going to be. Oh, I might be able to post this. So this is the solution 3. This is solution. This is the third solution of the official solution. using NumPy and convolution. So this is the problem, is basically convolution. And convolution of two matrices can be obtained, right, in NumPy via dot product. Yeah. Thus, we just need to expand one of the images, right? Expand one of the images, and then let the other image move around the expanded image. And then use convolution, right? Convolution to find the number, and use dot product to find the total number of overlapping ones. Okay, n equals len image 1, and 1 equals numpy dot array image 1, image 2 equals numpy dot array image 2, right? So as we get these two, we're going to say padded 2. Right, padded equals numpy dot pad. Actually, I don't know, so I'll have to check numpy dot pad. NumPy pad. Yeah, the reason I don't remember this mostly, just I never write it, so I have to write it. Pad width mode. Pads with constant value, which is default. We need a const values. Default is 0. Wait, what's the second one? Pad width. To the edges of each axis. Okay. Constant value 4 and 6. Oh. Holy crap, this thing is complicated. That's what we need, right? A2 pad width. So I think I just need one value. Medium, maximum, and value. Linear ramp. Const value. Which is at this side and this side. You know what? Need to we need to play around with this. Okay, so A equals numpy dot array. Let's do, what do we do? 1, 2, and 3, 4. Right, for the current case, I only need to numpy dot pad A. I want 2 and I want 0. I'm going to say constant values equals 0. Does this work? Yep, this works. So we use the easiest one, pad image 2, okay, and we're going to do n-1, the number I'm going to pad out, and a constant values equals 0. Okay, so this is padded. now we're just gonna go for I in range 2 times n minus 1. That's the same as my solution. 2 times n minus 1, right? Now we go through. So we're gonna say padded kernel, right? So kernel is gonna be padded. So we say, ooh. Oh, gosh. Hold on. So basically we say we'll go through all of this and I'm going to shrink it to this, right? So the I should be, I don't know, this and then this, right? This, we're going to do this. So I don't think it's 2n minus 1 though. 2n minus 1 will go all the way down. Then we don't have, because we just take the top left corner, right? If it's the top left corner, it's going to be, hold on. Right, we have this, this, and at the end is this, right? So we start with this, and now we can get this. Everything, yeah, everything. And this should be the end position, right? Ah. No. Oh. It's n minus 1. Oh crap, it is correct. It is correct. My bad. It is correct. Yeah, that's how much you can move. That's how much you can move. Yes, that's correct. So padded. So what's this? From where to where? Well, from I, right, to I plus n, and j plus that's not that bad. So kernel, right, and then the rest equals to 0, and then we say res equals maximum res and kernel times image 1, and then we return res. Let's see. It's not defined. Of course it's not defined. No, import. That is interesting. There's not a value? What? They're using dot product, right? the sum. Huh. It is matrix multiplication. Hold on. Actually, I'm not sure. B equals A. A times B. What's A times B? 1, 3. What's numpy dot AB? That's multiplication. That's why it says use matmul or this one instead. So this, yeah, we have to go. It's not dot. It's not dot product. It's piecewise, right? It's piecewise. Via piecewise product, which can be achieved by using just multiply symbol. Okay, so we have to multiply and we have to get a sum. Fine, I'm okay with it. Yep. Oh my god, this one can be slow. Shoot. And I think this is O into the fourth, or I just follow its course. Alright, as the last one. Anything that's not in the official library is not. Oh, this might be the fastest. Alright, that'll be it. I think I will put my thing there as well. Here's convolution. Alright, that'll be it. I'll see you guys tomorrow. Adios.